check their ID yet because they may not bring. But Thursday, and after that, you check ID. Last time we stopped here.
Did you want one form or two forms of ID?
What?
One form or two forms of ID?
Just one is enough. Just one is enough. You don't want two forms of ID. Last time we finished this, okay? Minus W equal to integration of VDP. Rohan Agrawal. What is minus W? That's Rohan Agrawal. Rohan Agrawal. Not here yet. Okay, second one. Simon C. Achoku. Simon C. Achoku. What is minus W? Can you speak up a little bit?
Minus W is what else?
Minus W is?
Yeah, the what else?
The work done on the system.
Yeah.
Whenever we have the work done on the system, then we have minus W. Okay, so W is the work done. Is it right? Work done by the system and work done on the system. Let me check a little bit. Okay. Oh, W is work done by the system. So minus W is work done on the system. Thank you, Simon. We go over the adiabatic process, two-stage compression. Today we are going to do derivation. Afshin, Arabian, Amar. Afshin. Afshin is not here. Okay. Foster R. Anderson. What is the reason that we need to know about the derivation, Foster? To understand how it works. Good answer. Okay, let's go over it. So for isentropic process, we have PV to the power of K equal to constant. Okay. That K value is, so when we have this, what does it mean? PV to the power of K. Isentropic means what constant? Which one? Mobile J absent. Isentropic means what constant? What? Which one? Enthalpy, pressure, temperature, volume, or what? Isentropic means what stay constant? Enthalpy? Capital H? Enthalpy? Yes?
Yes.
I disagree. Isentropic means constant S, entropy. Okay, that's isentropic. Those words, it could be in the answer question on exam or something. You need to memorize that. You remember the very first page, we talk about isobaric process, isentropic process, all that. Please memorize before the exam. Alright, when we start from that, I take the PV to the power of K. If you take a look at it, PV to the power of K, very first slide. Okay, this one, right? If n equal to K, we have constant entropy process. PV to the power of K equal to constant means S doesn't change. So that is a theoretical horsepower derivation. Okay? Theoretical horsepower derivation. So I take the derivative, put the operator on both sides. Put D over there, put D over there. Okay? D of A multiplied by B is AdB plus BdA, right? So that's what it is. Divide the whole thing by V to the power of K. We get this equation. Rearrange it. Okay? We get this one. Integrate it from condition 1 to condition 2 on both sides. Stirling R Aldrin. What is condition 1 and what is condition 2? This is the derivation of analytical method for isentropic horsepower. So what is the condition 1 and what is condition 2? Oluwadamila W. Bane. What is condition 1 and what is condition 2? You have seen the compressor, right? Compressor to what? Compressor gas. So condition 1 is before or after the compression? Before. Very good. So condition 1 is before the compression, condition 2 is after the compression. Okay? We compress the gas. So when we integration limit is from condition 1 to condition 2. We put that on both sides. Integration of 1 over P dP, we get natural log of P. Okay? We get natural log of P and substitute the integration limit. Condition 1 we have P1, condition 2 we have P2. Put it in, we get that. So integration of 1 over P dP get natural log. This kind of thing is calculus 1 and you expect to know this because it is used in the derivation. Okay? When we integrate it, rearrange it a little bit, remove this log thing, put K to the power of this part, both sides raised to the power e to the power of each of these, then we get this equation, right? Okay, P2 over P1 equal to V2 over V1 to the power of minus K. Keep in mind that this is isentropic process. If we compress it, when the entropy stays constant, we can have this relationship. Otherwise, we don't have it. Okay, otherwise we don't have it. Okay, after we have this relationship, we start again from this equation after we rearrange it. So we integrate both sides. Integration from 1 to 2 on both sides. I move V over there, move P over there. So I integrate it from condition 1 to condition 2. And this time, you see this PK. So P, instead of writing P, I put P equal to P1 multiplied by that ratio. Okay. Instead of writing P, I can say P1 multiplied by V over V1 to the power of K. Okay. I substitute the value that I already have. That one. So when I have that, I know that minus W is integration of VdP from the previous formula that we get together, right? From previous slide. Okay. So substitute this one on the left hand side. We get minus W equal to, okay, look at right hand side carefully. You see this K? It's there over there. P1, we say, hey, P1 and V1 to the power of K is a constant. It doesn't change from condition 1 to condition 2. Think about it. Suction pressure doesn't change, right? Suction pressure stays the same. So I can take it out of the integration sign. What about this K? So this K comes from here, right? I take that K out from the integration. This means that K value, K of gas is a ratio of Cp over Cv. It is a fluid property. So I assume that it is constant from condition 1 to condition 2. So when I move the piston, even though gas gets compressed more, but K stays constant. Ryan L. Baxter, is that true? Do you think K stays constant?
Should.
It should. Okay, memorize your answer and we will take a look at it after a while. Okay, it should, right? So after we get this equation, I copy to the next page, which is this one. Okay, integration of V to the power minus K is V to the power of 1 minus K divided by 1 minus K. Just calculus 1 integration, right? If it is appear in the test, I don't give you the formula because I think it's too easy for a senior student. Okay, you can do it. Substitute the value for condition 2 and condition 1, I get that minus sign. Alright? And I multiply V1 to the power of K on both terms. Then I get this equation. Okay. Now I try to just rearrange it. I know the relationship between pressure ratio and volume ratio. Okay. Then I know that, hey, volume ratio should be pressure ratio to the power of minus 1 over k. I put it inside. Then I get this. Okay. Just substitute the value that I know. And rearrange it a little bit. Okay. Then I get this equation. So I convert ratio of volume to ratio of pressure and combine the term by use the formula that we already have. Okay. When I look at the unit, okay, this is almost the final form, but it's not the unit that we like. W is work, right? Which is power force foot. Power force foot is work. But when we try to get horsepower, we want HP, okay? Work per unit time. We don't want work, we want work per unit time. So this equation tells me that if I start from pressure 1 to pressure 2, I compress it. That is the amount of work that I need to add into the system, right? Minus W is the amount of work that we need to add into the system. I define W bar as work per unit mass. Okay, W bar as work per unit mass, and then I have unit of W bar as that. Power force foot per pound mass. Okay, and from PV equal to nRT, we have N can be expressed as mass over molecular weight, right? So I rearrange it, substitute this equation in. I have W bar equal to, so you can think about, instead of volume, you see this volume, instead of V1, I put nRT over P, okay, instead of V1. And then I have, instead of P1 V1, instead of P1 V1, I put mRT over molecular weight. So I put mass on another side, and I keep RT over molecular weight, like that. I substitute the value. This time I use a little strange value for gas constant, which is that much power force foot per Röntgen per bar mole. Okay, and molecular weight I can express it as in specific gas gravity. Then I put everything in, I get that equation. Okay, this equation is the same as what we have in ICOCO, one of the reference. For real gas, instead of just 1 minus 1 over k, ICOCO suggests put that compressibility factor over there. Okay. And now we have work of compression per unit mass. It's not quite done yet. We want horsepower. Okay, let's rearrange it a little bit more. Okay, I can mass, power mass. So the unit of power mass is kind of, if we have standard cubic foot per day, that is equivalent to mass flow rate. You agree? You can have the conversion between mass flow rate and standard cubic foot per day. Okay, I do some rearranging, substitution. Finally, I get this equation. Okay, so this equation tells me how many horsepower do I need per the flow rate of million standard cubic foot per day. Okay, if I want to do the compression, start from P1 and end up at P2, okay? And temperature at the input is this much, okay? TB is the base pressure, PB is the base, PB is base pressure, TB is the base temperature. So we use what? 14.7 and 60 Fahrenheit, right? That is like pressure temperature at standard condition. P1 V1 is the suction pressure. P2 is the discharge pressure, PSI A and PSI A. Z1 is the compressibility factor at suction condition. K is the ratio of CP over CV. Okay. So this equation is have that Z1 added in compared to the previous one, just that. The rest is kind of the same. Okay. Now let's talk about compressibility or K value, Cp over Cv. How many people do we miss? One. Rohan Agrawal? Just him, right? Okay. For ideal gas, Cv, specific heat capacity at a constant volume, is specific heat capacity at a constant pressure minus R. R is gas constant. That's for ideal gas. And everything has to be the same unit. So R, it has the same unit as specific heat capacity. If you don't know now, memorize it. Okay? R has the same unit as specific heat capacity. So Cv is Cp minus R. And for ideal gas, we have K over K minus 1 equal to Cp over 1 over something. Alright? That's ideal gas. For real gas or natural gas is a combination of several gas, right? Natural gas is a combination of several gas. So what we do is we find mole fraction of each component, we find the molecular weight of each component, we find the specific heat capacity at constant pressure of each component, and we average it by use K mixing rule, and we get new K value of natural gas. So if my gas have multiple components, I can add them together like this. Good? Okay, now question is, how do I get all these things? Cp of each gas. I buy what? American Gas Association handbook. And then I open some page, then I have that, okay? You have to buy the book to get the chart to tell you this kind of value. Otherwise, I Google it, okay? And when I Google it, it leads me to NIST webbook that do some calculation for me. We will talk about that in a minute. Okay, we can do some approximation. It's a quick approximation. Use this kind of formula, okay? So this will give me ratio of Cp over Cv at 100 Fahrenheit for natural gas, where specific gravity stay from pure methane and pure air, okay, from 0.55 to 1. Put the value of gamma over there, take that log, log. Clara M. Benavides. What is that log log? Is that log base 10 or base E? Base 10, correct. Very easy, right? I think 4 years ago, there was one student asked me in the exam room, that log, where do I put it? Is that log base 10 or base E? I say I don't answer any of that, okay? So you should know. Okay, next step is, what is the discharge temperature? For theoretical discharge temperature. So in theory, discharge temperature actually depends on if we use centrifugal compressor or we use reciprocal compressor. Centrifugal compressor just spin, okay? Receive unit just push back and forth. If we use different type, the coefficient, I think we need to have 1 over eta is different. But this equation is for ideal case. So theoretical discharge temperature, without considering the compressor that we use, we get T2 over T1 equal to ratio of pressure to the power of Z, K minus 1 over K or something. So we can tell the discharge pressure directly if we know what is the compression ratio. You still recall about the compression ratio? Compression ratio next to Clara is Jeremy and Bilisek. What is compression ratio? What is the formula for that? Is that ratio of pressure or ratio of volume? or ratio of temperature? Pressure. Yes. I know that you have what senior design and everything occupied by senior design thing, right? Compression ratio. If we go previous slide. Where's that? Compression ratio, PD, OPS, P discharge, OP suction. Okay, it should stay between 3 and 4, and use absolute pressure to do it. For example, 0 psi-G, you have to convert to psi-A before do any compression ratio calculation. You recall that? Good? Okay. R, compression ratio, is a ratio of pressure discharge over suction in the absolute unit. Once we know that, we can predict what should be the output temperature. So the reason that we need, that it is very important to know this part is, sometimes we may be able to compress it very hard, but if it is too hot, it will burn the equipment or melt the equipment. I think last year I see the compression get burned. I think that's in CSI or Highborn. They show the compressor, big compressor, the engine got burned. Okay. So that is theoretical discharge temperature, and there's a safe limit that we talk about. What is the temperature that we should go above? Okay. Heat removed by cooler, delta H equal to NCP delta T. So CP is a constant pressure, molar specific heat at cooler operating pressure, average cooler temperature, blah, 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 blah. So this tells us how much heat we need to remove to get the desired temperature. Let me give you an example. If we move from 100 Fahrenheit, we compress it. Isentropic horsepower. Let's go back. Remember this chart. So we stay at point A, we compress it. Constant entropy, as constant, we just go up, right? We just go up to point B. Then we stay at B. Then we have to cool it down. To cool it down, we need to use aerial cooler. Reduce the temperature while pressure stay constant. And actually you already used that kind of equation, which is the N delta T or something. You remember that in the example? Okay. So if we use the chart, we just read the difference. Okay. After I get the difference, I can tell what is the difference in enthalpy. Then I multiply by bar mole. Then I know how much heat I have to remove. Right? Okay. That is the same as this equation. The difference is, in this equation, we get delta T from theoretical value instead of the chart. Okay, that's the difference. So there are two methods to get temperature. Look at the chart, or use this formula. Okay. Okay, K value. Previously showing that. Is it? Ryan? Where's Ryan? Ryan Baxter, right? You said it should stay constant. I think so. I think it should stay constant because from the correlation that I have, I get this kind of equation. So this equation tells me it's not quite dependent upon temperature, not pressure or anything. It just depends on CP value or something. Okay, and this equation, now you may see, hey, why should it be 150? Can it be something else? Yes, it can be something else, but if it is something else, it changed. I think we talked about that a little bit. Look at this. I plot CP over CV versus temperature, and you see that it changed a little bit. It's from like 1.33 to 1.23. Okay, when the temperature go from 50 Fahrenheit to 400 Fahrenheit. Okay. And when I change pressure, Interestingly, it go up and go down a little bit. Okay, this is for the case of pure methane, getting the value from NAST vapor. So this means that what we did previously, that I take K from there outside, assume that it's constant. Not quite true, right? You agree? So because the data show that it changed. Emily M. Billingsley, what do you say about our derivation? I take it out, but later on I show that K should not be constant. It changed with pressure. What do you say about this derivation? Is it invalid? We trash everything or what? What do you say about it to make other people see that okay, it's reasonable? We did something that mathematicians won't do, right? We take K out. What do you say, Emily? What? We have to say something that makes us look good, that we do this and it's valid. We have to give some reason why is this valid. So what we get, even though it's not precisely correct, like what mathematicians want, but it's a good approximation. Memorize this, okay? We don't trash it. It is a good approximation. Best solution that we have within available resource. This formula leads to, of course, something that is wrong. This is not perfect. I don't call it wrong. But it's better than don't have any formula. What do you think? True? If we don't do any of that, we don't have any formula, and how do I guess the horsepower per million standard cubic foot? I cannot say anything. And we already know that isentropic horsepower is somewhat less or more than the actual horsepower required. Emily? Less or more? Isentropic horsepower from the theory is that less or more than the actual required horsepower? What's that? What's that? I don't understand. When you do this, see, you remember this? Less or more? Area under the curve is work, right, required to do the compression. And S, that is theory. And another one is actual. So Emily, isentropic horsepower, is that less or more than the actual required horsepower? Less. Thank you. Correct. It is less. Okay? Actual horsepower will require more than the theoretical horsepower. But we know for sure, if anyone tell me to buy something that is smaller than the theoretical requirement, that is wrong. Obviously wrong. But if it is more, I don't know if it is enough or not. Okay? Oh, here's the heat required equation. Delta H equal to N delta small h. Alright, let's continue. We get a good equation and we try to compensate on the imperfection that we have by put that thing over there, compressibility factor. And it gives me a reasonable prediction of required horsepower. Let's do some example. Adiabatic reversible expansion. Next. Corner P black. High corner. What is adiabatic reversible process? What state constant in that process? Entropy, enthalpy, pressure, volume, or what? Did you come last time? Yes. We talked about that, did we? Adiabatic reversible process. Okay, to recall our memory, let's take a look at this. Do you find something interesting in this slide? What is adiabatic reversible process? Constant entropy. That is the question on the quiz couple times last year. Okay. Constant entropy, constant S. I want you to know that it is a reversible adiabatic process. Adiabatic means no heat in and heat out. And if it is reversible, this means is constant S. Isentropic process. Okay, isentropic process. Good. So the example that we have over here. Okay. Next to corner. Oh, what's the name? Benedict. Could you please come to the podium and help me read this? Just the question part. Thank you, ma'am. It's just reading, man. Why don't we read the whole thing? Okay. Read the question, then you pause, and then read the solution. How about that?
If a 0.7 specific gravity natural gas at 300 degrees Fahrenheit and 500 psia is expanded adiabatically and reversibly to 100 psi, what will be the final temperature of the gas?
Solution to
Using the HS diagram for 0.7 gravity natural gas at the intersection of the 300 Fahrenheit and 500 psia lines, the entropy S1 is negative 2.5 BTU per pound mole Fahrenheit. In an adiabatic process, no heat is added or removed. Since the process is irreversible, Q is equal to integral of TdS equals to 0. Or ds is equal to 0 and S is constant. The reversible adiabatic process is isentropic. By following the entropy line of S1 to its intersection at 100 psia and read the temperature we got, T2 is equal to 105.
You understand?
I have to read it again now.
Thank you, ma'am.
So the example here is asked to use a graph. If we go from 300F, 500 psia, it expand and move down vertically to 100 psia. What is the final temperature? Okay. And is it going to be hotter or cooler when we expand it? Typically, is it going to be hotter or cooler? Kind of cooler. Okay. Because the solution here say 105, but we enter at 300, so it's cooler. So this is adiabatic reversible. So what I do is I start at that point, 300 F, 500 psia. You still know how to use model diagram, right? 500 psia line is that line, okay? And I go down vertically because it is a constant entropy process, okay? Adiabatic reversible. Then we go down until I meet another line, 100 psia. Then I read the temperature. The temperature is 105 Fahrenheit, just that. Thank you, Benedict. Carson B-boy. Carson. Oh, we have to, okay, Carson. What about flow through a choke? Is it like this? Constant S, true or false? Or flow through a choke? False. Correct. For flow through a choke, thank you, Carson, we have constant enthalpy. It is not reversible. Okay, flow through a choke is not reversible. So when we have flow through a choke, if you remember, we move horizontally, but this time we move vertically because the example here says very clear that it is adiabatic reversible expansion. Okay, if we expand by flow through a choke and expand by flow in the adiabatic reversible process, which one do you think we get cooler temperature? When we go this way or we go down? Or we just leave that for the exam or something, okay? Let's continue. 3.8, throttling or Joule-Thomson effect. Some people say Joule-Thomson cooling, but yeah, we can say that most of the time. Maybe 5% of the time, when we have expansion, it can be hotter. Okay. Typically, when gas expands, it is cooler, right? It's getting cool. But for very, very high pressure, pressure drop can make gas hotter. Okay. That is the indication from this Euler diagram. It curves a little bit, and this part, see, it curves down and up. So if I go through a choke, move horizontally, I move from 10,000. So I move this way. The temperature go up a little bit because this constant temperature line is like an S curve. So this part of the curve, very high pressure, when it become, let me redraw it. When it bend like the S shape, okay, constant temperature line, whenever it is kind of S shape, when we decrease the temperature, it can get a little hotter. This place will be more obvious, but that's a rare case. Most of the time, pressure drop, it's getting colder. So that's why we call JT cooling effect, right? Okay. So Joule-Thomson effect, if gas of 0.8 specific gravity at 2000 psia and 200 F expand through a small orifice without addition or subtraction of heat and is brought finally to its initial velocity and pressure of 50 psia. What will be the temperature? Random edge breathing. Why do we have to say anything about brought finally to its initial velocity? What does it tell you? Lambda. Delta what equal to 0? Do we gain in velocity? When the example say it's brought finally to its initial velocity, what does it mean? Do we gain potential energy? Kinetic energy? No kinetic energy, right? We don't need to consider the change in energy due to the change in velocity. Velocity kind of stay the same. So this is to say, hey, just use the chart. Okay, this is brought finally to its initial velocity. This just to say that the chart value will be correct. Okay? In most cases, throttling process occurs so rapidly and in such a small space that there is neither sufficient time or nor large enough area for much heat transfer. Therefore, such process may be assumed to be adiabatic, but they are not reversible. Okay, adiabatic but not reversible. So follow 700 BTU per pound mole from 2000 to 50,000. Read the temperature. We get T equal to 100 F. So this time I move horizontally. Okay, horizontally. So from what? 2000 psi. Move. That's a starting point, right? That's starting point. Move horizontally. Use the chart. Then finally I reach at that point. And at 100 F, 50 psi. Then I read the temperature. I end at 50 psi and I just read the temperature. So this is constant edge or constant enthalpy process. Good. Isothermal expansion. For isothermal expansion, we move through the red line, constant temperature line. Okay, we get the difference in enthalpy. Then we can do the calculation. Okay, how much BTU per pound mole has changed. Okay, read it more, and we quiz you later or test you later. And 3.11, okay, 40 million cubic feet per day measured at standard condition at that temperature, flowing freely through an expansion valve with pressure drop from 2000 to 1000 psi. What is the temperature change across the valve? What is the maximum work that could be delivered from this expanding gas stream without using heat? What would be the temperature change on the gas when expanding through adiabatic reversible engine? Okay. Throttling process, enthalpy is constant. So this is like a hydrate thing, right? Choke in the line heater. So you know how to do that already. So we move. So we just need to use the shaft and we move horizontally. Then we can find that part. When I say adiabatic reversible, we go down. We do a little bit more calculation, okay? And the difference may be maximum work. Okay, this part may be new. Using adiabatic and reversible process, isentropic process, maximum work could be what? So I get delta H, right? After I get delta H, this is 840. Delta H is different. Okay, that's 840. 1400 minus 560. The unit is pound, BTU per pound mole. I had to do some conversion. So I think we have gone through this already, did we? So we need to know relationship between pound-foot per second and horsepower. So 550 pound-foot per second equal to 1 horsepower. And 1 BTU is 778 pound-feet, right? So then we know 1 horsepower equal to that much BTU per hour, 2500 something. 1 pound mole, we can use a gas law. 1 pound mole occupy that much volume. Okay, so we know the flow rate, do we? So we know the flow rate, 40 million cubic feet per day. So that's the flow rate. So we know the flow rate, 40 million cubic feet per day. So I put 40 million. Okay, do some unit conversion, then I get, okay, for that difference in the enthalpy, this much expansion can deliver maximum work of that much horsepower, 1400 something. Okay, I think you can do it. N. Question? No question. Stuart W. Bruce. Is it okay to have this in the exam?
Yeah.
Okay, all right. Thank you. Is it okay for everyone else? Yes?
Yes.
Yes, okay, so thank you very much. Right. Let's move on to the next part.